Okay. Greetings, everyone. Today, I'm here to present you the paper that we wrote with Professor Koychev on the topic of generating phonetic embeddings for Bulgarian words with neural networks. As we all know, word embeddings are considered the cornerstone of modern NLP. Most embeddings model the semantics of words, so the meaning. And during my master's thesis, we asked ourselves, okay, can we have embeddings which model the way a word sounds? So if we would go in that direction, we would need a model that would work on phonemes instead of graphemes. The answer is yes, we can create such embeddings. We used a fairly straightforward transformer model, which is fed a word, the word Bulgarian word, which is split into syllables. Then the model has to output the transcription of each syllable before the syllables are then connected back to a single word. And the main thing I want to highlight here is that we take a word, we split it in syllables, and we work with each syllable separately. And the output, again, is a set of syllables that we can connect together again in the right order. For the data, we extracted a few books from the popular Bulgarian site chitanka.info. 5 books were correlated, each in a separate text file. Then each book was transformed into sentences and then into words. For every word, we extracted the emphasis of the word. So because the emphasis changes the way syllables are transcribed then, we needed that as well. And for each word, we split it into syllables and manually generated the transcriptions that were fed into the model. So you can learn. And we see we have 6,000 words and transcriptions together to fit into the model. This is our first experiment that we did. Basically, we gathered 15 Bulgarian words, fed them into the model, and we saw, okay, what does the output of the model look like? If you look carefully, almost all the transcriptions are correct, except for the word chasovnik, which means clock. There, the model got it wrong. I think if we take that transcription that is generated and put it in Bulgarian, we will get something like chayasnik or something like that, which of course means the model went wrong, at least on one word. However, this is only 15 words. We decided, okay, let's test it on something bigger. And how do we evaluate such a model? Well, as I said, we are working on syllables. So the first metric that we did was to take the Jacquard index and basically compare if the sets of syllables in the actual word is the same as the set of syllables in the predicted word. And we have 2 examples here. With the word благодаря, all the syllables are correct, so the score for that word is 1. While for the word разцъфтях, we have some differences, and the Jacquard score is 0.75. Over the whole testing data set, we got 99.751% match, which I think is really good for such a model. However, this metric has one drawback. We don't consider the ordering of the syllables themselves. We just check if the syllables are correct. So that's why we introduced the second metric, direct comparison, which basically goes through syllable and check if the current syllable is in the right place compared to the actual word that we should predict. Here we can see again the word благодаря, разцъфтяха, and another word примерен, where we see that if we have the same syllables but in different places, this metric will yield a lower score. And again, on the test dataset, we get 99.285% match, meaning that there's 0.2% of words that have the correct syllables but in the incorrect places, which was interesting to me at least. However, this is just a transformer model. What can we do with it? Well, we can take the embeddings that are generated by the encoder, and we can use them to perform some task and see how they measure up. Again, it's very important to mention we have multiple embeddings for a single word. So if we have a word from 3 syllables, we'll have 3 sets of embeddings. The first task that we try to accomplish with those embeddings is the paronym detection. 2 words are paronyms if they are close in sound but different in meaning. As an example, in Bulgarian, the word statistic and statistic are such paronyms because they sound really similar, but of course their meaning is completely different. And we ask ourselves, okay, using those embeddings, can we create a model that predicts if 2 words are paronyms or not? Of course, when dealing with embeddings, cosine similarity is an important metric used everywhere. We compare each vectors, we compare the length of the words in the given formula, and we get a metric how close do the two words sound. From there, we created a small data set with 185 words, 92 paronyms and 92 non-paronyms. We split the data set and we created a simple logistic regression classifier to classify if two pairs of words are paronyms or not. And this is in the first column, you can see the results using the accuracy, precision, recall F1 metric. And on the right, we trained the same classifier, but this time with the fast text embeddings. And as we can see on the accuracy, we have similar results to fast text. Precision is a bit lower for our phonetic embeddings. However, the recall is higher. And the F1 score is a bit higher for our embeddings. So at least for the paronym detection task, our phonetic embeddings perform slightly better than the fast text ones. The second big task that we try to accomplish using those phonetic embeddings is the language of origin detection. Considering that we now have embeddings which model how a word sounds, we can try to determine if a word is from Bulgarian or from Bulgarian from any other language, which is used successfully in an algorithm to detect loan words in Bulgarian sentences. For there, we created an RNN classifier, which takes a word, splits it into syllables, gets the embeddings, and then it classifies it based on the language of origin. 3 linear layers in the model, each syllable is passed through the model. We keep the hidden state and we pass it for the next syllable. At the end of the word, we get the top 5 most probable languages of origin for the given word. The data set we collected from 2 loanword dictionaries. We have 5,000 pairs of words. And from there, we created 3 sets of data, depending on how many non-loanwords or Bulgarian words we put into the data set. We have 5,000 Bulgarian words, 13,000 and 30,000 Bulgarian words, along with the 5,000 loanwords. So we have those 3 data sets to model basically how much loanwords we put. And so from there, we have 3 models, and we compare those 3 models with BGGPT, ChatGPT 4o, and again, same model, but with the fast text embeddings. Here we can see that the metrics rise the more Bulgarian words we have in the data set. However, this just means that the classifier just predicts every word as Bulgarian, and of course, it will perform better the more Bulgarian words they are. What was curious to me was that our phoneme loanword embeddings and classifiers performs comparatively to BGGPT, which is a much larger model, and also not that far away from ChatGPT, which of course is an even bigger model. Compared to fast text, we are a bit behind, unlike the paronym detection, but I think there is much room for improvement in our model. Again, basically we don't take some things into account. The main one being is the difference between similarly sounding syllables. For example, ma and na should be way similar than ma and po. However, the embeddings prove that they do not exhibit this property. So this is something we could probably work on. And of course, if you have a word with 2 syllables and you have another word with those 2 syllables and the second one repeated again, distance is not consistent. So in some cases, when you work on word level, the differences are not that consistent. And of course, this model was developed only for Bulgarian currently. However, it is possible to extend it to other languages. And as a conclusion, basically we built embeddings which model how a word sounds, which are successfully used in paronym detection and language of origin detection. Thank you.